And I'm going to stop the recording for a second. Well, no. Okay. Okay, so we have two vectors in R2. And we want to find, say, this angle and this angle. There's a simple rule for finding the angles. Well, first of all, okay, V1 is 7, 2. Okay, the magnitude of V1 is, by the Pythagorean theorem, square root of 53. Okay, and you can see that, and it's important to see that in terms of a triangle. I can draw a triangle here. It's a right triangle, and this side is 7, and this side is 2. So this side must be the square root of 53. And I'm assuming you're totally familiar with the Pythagorean theorem. If not, you really need to review that. Okay. Then the magnitude of V2, well, we could draw a triangle for V2. We could draw a triangle, let's say, down here. And it's a right triangle. And you have a side of length 4 here. And 6 here. So that the magnitude of this is a square root of 6 squared plus 4 squared. I believe that comes out to the square root of 52. And let's be formal about it. It's the negative 4 that we're squaring, the two components. This equals the square root of 52. As a Pythagorean theorem, it generalizes. We had a vector with 4 coordinates. Let's say we just had a vector not related to these, but in R4, the vector was 7, 2, 6, negative 4. Then the Pythagorean theorem would easily extend to say, well, then the magnitude of that vector, the length of that vector in 4-dimensional space, if you wish, is square root of 7 squared plus 2 squared plus 6 squared plus negative 4 squared. And of course, adding up all those squared, you'd end up with 105, 53. So the magnitude of this 4-dimensional vector in R4 would be the square root of 105. Very easy, just an extension of the Pythagorean theorem, almost exactly what you would expect. And we could explain why, but this is not introductory trig class. Just going over the well, we're not going to develop that right now. We might refer to it a little later, how we extend the Pythagorean theorem into 3 dimensions with a 3-dimensional parallelepiped and the diagonal of that parallelepiped. Hopefully you've seen that, but maybe not. Okay, well, we have these two things, okay? Now the angle is the arctangent of 2/7. That's theta 1. Okay, you can calculate that. You put it in your calculator because you don't have a way of actually calculating it by hand. And we didn't back in the old days. We had thick tables in very fine print that you would use to figure out what the arctangent of 2/7 was. It can be approximated. That's around 0.3, so it's around 18 degrees. But give or take a degree or two. Okay, theta 2 is the arctangent of -4/6. And that turns out to be a negative angle. I'm deciding just how much detail I want to go into this. The arctangent of -4/6 is negative because the arctangent of a negative is a negative angle. So you'd have a negative angle go down like this, but we're doing it between 0 and 360 degrees. Since the arctangent is negative, we're going to deal with positive angles from the positive x-axis. Okay, well, and why is that? Because the definition of the tangent is opposite side over adjacent side. So the tangent of this angle is 2/7. And if the tangent of this angle is 2/7, then the angle is the inverse tangent of 2/7. And hopefully we understand inverse functions. Another topic that is worth some review when you have time. Okay, so we have all that. And that's basic, first few weeks of a trigonometry class, just basic right angle trigonometry with the inverse tangent function. Okay, so we can calculate all that. So we can calculate, given the coordinates of a vector, in R2 at least, we can calculate the magnitude. And given the coordinates of a vector in Rn, we can calculate it, okay, just by extending the Pythagorean theorem. Now, what we can't do is we can't extend this calculation with the arctangent into higher dimensions. And that you get what's called direction cosines, and I don't want to talk about that just for brevity and for, again, the idea that, that this isn't a trig course, and it's not a multivariable calculus course. So we're just going to kind of generalize the thing about angles. Now, with that background, we define the dot product of V1 and V2 as V1 dot V2 equals, I'm going to do it as a vector product. I write V1 as a row vector and V2 as a column vector, so that these vectors are compatible for multiplication. I can't multiply this vector by this vector because you can only, well, I can, but you don't get what you get if you do one as a row, the other as a column. Okay, well, that then clearly equals 42 minus 8, which is 34. And I could also alternatively do V2 dot V1. And in that case, I would write V2 as a row vector. And that's going to equal, that might not be any surprise, but exactly the same thing. Because why? Because you're multiplying either way. You're multiplying the first number here by the first number here, and the second number here by the second number here, and then adding them. Okay, well, that's dot product. Now, big deal about dot product. Okay, the dot product of V1 and V2 is the magnitude of V1 multiplied by the magnitude of V2 times the cosine of theta, where theta is the angle that V1 makes with V2. So now this is the definition of the dot product, incidentally. I mean, it can be taken as a definition. This could be taken as a definition, or this could be. If this is a definition, then it has to be like this. And if this is a definition, it has to be like this. It's pretty easy to solve if you know the law of cosines. Not going to assume that and not going to go into it, but that's how it comes about. And I believe your book tells you how that works out. So you might have to hustle a little bit with that basic trigonometry, which hopefully will come back to you quickly. And really, it's, I mean, much to your advantage that it does, because you need it in your curriculum. You're going to need all that trigonometry. At least if the curriculum is set up the way I think it is. There's some options within your curriculum. It depends what kind of engineering you go into, how important this is, but it's important no matter what. Okay. So anyhow, this is what we mean by dot product, or if you like, this is what we mean by dot product. They mean exactly the same thing. It's just two different ways of looking at it. Now, because of this, if we know V1 and V2, as we do here, we know what the magnitude of V1 and V2 are. And we know what the dot product is. The dot product here is 34. Magnitude of V1, magnitude of V2, well, there you have them. So if we know this and this and this and this, we can find the cosine of theta. And once we find the cosine of theta, we can do the inverse cosine of that and find the angle between these two vectors. It's very straightforward, very simple calculation, and it works the same way in any number of dimensions. So you can always find the angle between two vectors in R12 if you want, whatever. Okay, so anyhow, here's our dot product. And it follows from what I've written here. Cosine theta, very easy to solve this for cosine theta. You just divide by the magnitude of V1, magnitude of V2. It's V1 dot V2 over the magnitude of V1 times the magnitude of V2. And this is always true. Okay, well, in our example here, V1 equals 7.2, V2 equals 6, -4. What do we have? We have cosine theta equals V1 dot V2 over the magnitude of V1 times the magnitude of V2. And V1 dot V2, as we saw, is 34. Magnitude of V1 is the square root of 53. Magnitude of V2, coincidentally, and I didn't set it up this way, but it's real close, it's the square root of 52. Okay, so this is approximately equal to 34. Now you could do this in a calculator, but if it was a square root of 53 times the square root of 53, you would just get 53 for the denominator. This is the square root of 52 times the square root of 52, you'd get 52. So I'm going to say that when you do these two square roots and multiply them, you got to get something really close to 52.5. Okay, now 34 over 51 is 2/3. Yeah, 17 goes into 34 twice, 17 goes into 51 3 times. A little less than 2/3. This adds approximately 0.65. Now, so theta equals the inverse cosine of 0.65. Now, I can't do the inverse cosine of 0.65 in my head, but of course, I know that the cosine of 37 degrees is about 0.8. The cosine of 53 degrees is about 0.6. So this is going to be about 3/4 of the way between 37 and 53 degrees. That's a difference of 16 degrees. So I'm going to say it's probably about 49 degrees. Okay. Now, I could be way off with that because, I never know what I'm going in my head here. It's getting more and more unreliable, but I can also do an estimate of this using a unit circle. Something else you should have seen, but we find that a lot of times trig courses don't do the most important thing, which is a circular model. Okay. They confine themselves to right angles and maybe a few non-right angles, but it depends where you had the trig course. And, also maybe what was going on in that class at the time. So anyhow, we can make an estimate, okay? Because the cosine of an angle on a circle of radius 1, this is a unit circle, is going to be the x-coordinate of the corresponding point on the circle. And if the x-coordinate is 0.65, that's about 2/3. So I'm going to say, well, one half is about here, 3/4 is about here, and 2/3 ought to be about here. Okay, so let's see. Here's for x equals 1. Here's for x equals 0.65. And right here in the circle is a point on the circle corresponding to this. And the way I've got it drawn with another, not the greatest circle in the world. On a good day, I can draw a better circle than that. On a bad day, it's much worse. This is just an ordinary day. Now, this angle here is, and leave myself enough boardroom, but it says inverse cosine of 0.65. That's this angle. And what's that angle look like? Well, to me, it looks like it's about 45 degrees. And given the uncertainties in the way I drew things as a freehand drawing, that's close enough to 49 degrees that I tend to believe the 49 degrees. Okay? You punch it into your calculator. But I think it's going to be within a degree of that. Okay? Okay. Ideally, you're in a position to understand all of this. But the most important thing is that you understand that by using the dot product and the magnitudes, Pythagorean theorem, obtained from the Pythagorean theorem, the Magnetorean theorem, whatever I was trying to say, is easily calculated, and you can do this on your calculator. Yeah, I was hoping it would. You're a smart guy. And if you had a good trig course, it should come back to you. If you did a lot of homework, yeah. So again, you want to review it, but here's the bottom line right now, okay? You really want to know all this other stuff around it so you actually believe what you're saying here. Yeah, there we have it. Okay. Now, does that make sense in terms of the picture here? Does this angle look like it's about 49 degrees? Well, I think that's plausible. Okay. Now, I know you don't have a great perspective on this part of the board, although it looks pretty good in what I'm seeing. Zoom somehow doesn't always pick it up really well. Now, this angle isn't directed. Okay, it's not from one vector to the other. It's not a directed angle. So I'm going to use 2 arrows on this thing. can say that the inverse cosine of V1 dot V2 over magnitude of V1, magnitude of V2, approximately equals 49 degrees, and the inverse cosine is this angle here. Okay, does that look like 49 degrees? Not that much. It looks a little bigger than that, but that's just because I didn't draw these vectors really accurately. If I do a right angle with this vector, it's going to come out like about here. And this angle is a lot smaller than this angle. At 49 degrees, you'd have 41 degrees and 49 degrees. So the picture isn't totally accurate, but if you take that into consideration, it's at least plausible. And I guarantee you, if it's all done accurately, and I don't guarantee that it works. Okay. Well, that's a dot product. Okay, the dot product can be done in higher dimensions. Example in R4. V1, 2, 3, 7, negative 4. V2 is this. V1 dot V2 is easily calculated. I'm not going to write it out, but here's how you write it out. Except you got, if you would do V1, it's going to be a row vector. V2 is going to be a column vector, but your dot product is going to be what? 2 times 5 is 10. 3 times negative 6 is negative 18. 7 times negative 2 is negative 14. Negative 4 times 5 is negative 20. So we've got a bunch of negatives there. So you're going to have negative 10, negative 24, negative 32. You can check me on that because I'm not even going to bother to check it. Okay, so negative 32. Magnitude of V1. And I'm not going to write out all the details, but 2 squared is 4. 3 squared is 9. 7 squared is 49. 4 squared is 16. And that's a square root of 13, 29, and that's going to be 78. Okay, and V2, I was going to add them up. I've got 25 here and 25 here. That's 50. Negative 42. Yeah, I could have done that. That's 10. 24. Yeah, it's 42. Thank you. Okay. Glad you're paying attention. Somebody needs to watch me. Okay, so V2, you got 25 here, you got another 36, which is 86, and 2 is 90. So I think that's a square root of 90. So the angle is, I'm not going to write out the formula, but it's V1 dot V2, which is negative 42, over the square root of 78 times the square root of 90. Now, these things aren't linear, but 78 and 90 are close enough that if I take the number halfway between 78 and 90, which would be 84, that's probably about what I get when I multiply these square roots. And that's really convenient. I didn't set it up this way because I never think anything through before I do it, just to keep myself surprised and alert. Okay, negative 42 over 84 is negative 0.5. So our angle, and let's lower the camera just a little bit. So the watermark doesn't wipe us out. So theta is the inverse cosine of negative 0.5. And just coincidentally, that comes out really nicely. Okay. You know, you can do it with just a right triangle in this case, because it's a special angle. If the well, it's the way it is. If the cosine is 0.5, that means you got like 0.5 here and 1 here. And that's half of an equilateral triangle, because you get 1, 1, and 1, which means that this angle's got to be 60 degrees. Now, the inverse cosine of negative 0.5 would be what? Well, on the unit circle, here's 0.5. Here's the inverse cosine of 0.5. Here's negative 0.5. Here's the inverse cosine of negative 0.5. And you see that the inverse cosine of negative 0.5 is 180 degrees minus the inverse cosine of 0.5. That's 120 degrees. Now, it doesn't really look like this in four-dimensional space, because we can't even visualize four-dimensional space. We do a hyperplane in four-dimensional space and intersect these vectors with the hyperplane. And that's what it would look like in the proper hyperplane. Okay. And we're not going to get into the geometry of hyperplanes and so forth. That gets really interesting, but it's not even part of this course. It gets into what you call differential geometry and little modal variable calculus. It goes a little beyond that if you want to really get into it. So, big adventure in mathematics if you want to follow it that far, but you might not need to. You probably won't if you stay in engineering. Depends what you're trying to engineer. Okay. Well, there we have a pretty good picture of what you can do with a dot product. Okay. Now, I guess I want to talk, okay, can you use this equation with more than two vectors? You can only do the angle between two vectors. Okay, dot product is only defined for two vectors. And that's a very good question. I'm glad the answer was that simple. That's it, okay? If you have three vectors, you can't even talk about the angle between them. Now, if you have three vectors and want to find the angle between these and the angle between another pair, and then the angle between the third pair, you can always do that. Okay, so anyhow, one of the big deal things you can do with dot product is determine whether two vectors are perpendicular. Now, that relates to linear algebra because it's super convenient to have a basis of your vector space where everything is orthogonal. And perpendicular is just orthogonal, confined to Rn, okay? So can you determine whether two vectors are perpendicular? Well, sure, it's really easy to do that. So, this board, it can't just disappear like that. Where in the world is it? Oh, there it is. Okay, but I'm probably not going to refer back to this one, so I'll just flip this one. Okay, make sure everything is visible on the camera. Okay. Are these is the vector 1, 2, 3, 4, and the vector these vectors orthogonal, okay? And clearly they're not, so I'm going to make it so that at least there's a question, okay? They're not going to be orthogonal either, but okay. They are if the angle between them is 90 degrees. Well, theta is 90 degrees, then cosine theta is 0. Well, if the cosine of theta is 0, then magnitude of V1 times magnitude of V2 times the cosine theta is 0. So V1 dot V2 equals 0. These vectors, V1 dot V2 is, well, your negatives are going to be -4 and -4, which is -8. 2 times 3 is 6, 3 times 2 is 6. Add that, you get 12. So theta is not 90 degrees. And vectors are not orthogonal. Try this one. Find V2 and I want to write the equivalent condition. Let's state this such that V2 is orthogonal to V1. And let's let V1 be plain old 2, 7. Kind of like the 7, 2 we started with before. Well, there's 2 ways to do this, okay? By inspection, that just means you look at it and see what it ought to be. This vector dotted with this vector is going to give you 0. If you reverse the coordinates and make one of them negative, then when you multiply them, this is going to be -14, this is going to be 14. Okay, so in R2, it's really easy to do this. Now, if there are 3 of these, you can't just reverse things and make it work out. And if there are 4, 5, or 6, it gets more complicated. So I'll say alternatively, we want to be able to do this by setting up some simultaneous equations, basically. Let's let B2 equal AB is orthogonal to B1 if and only if, IFF stands for if and only if, you've seen that. Only if the dot product, which is this, gives you 0. Well, this equation has infinitely many solutions. Let B be the free variable. If you know the value of B, you can determine the value of A that makes this true. Okay, then A equals something's wrong here. This vector is 2, 7, not negative 7, 2. I wrote down the wrong vector here. I wrote down this vector instead of this one. So I'm going to get a little sloppy here, but it's going to be 2A plus 7B equals 0. Okay. So if B is your free variable, and the step I should have written down is we're going to let B equal T. So we're going to do this in terms of the parameter T, as we've done many times before. Okay, if B equals T, A equals negative 7/2 T so V2 is AB, which is negative 7/2 T, T, since B is T, A is this. So it could be T times negative 7/2 1. Of course, T could be any number, and we could absorb into T a factor of 2, and we get exactly the same set of vectors if we express this as T times negative 7, 2. The T that you would use here would be half as great as the T that you would use here, but it doesn't matter since T can be any real number. So this is our general solution. Any multiple of negative 7, 2 is orthogonal to 2, 7. So by inspection, we just chose negative 7, 2. Well, if T equals 1 here, you get negative 7, 2. If T equals 2 here, you would again get negative 7, 2. But there's a whole infinite family of vectors now that we find is perpendicular to V1. So we can conclude deciding how to write this. I'll just say as long as t isn't 0, you get this vector that's orthogonal. Okay. Now in two-dimensional space, we can sketch this. Our V2 is 2, 7. V1. V2 is any multiple of -7, 2. And where's my blue chalk? So that's what I usually use. Okay. Well, -7, 2 would be like here. And the set of all multiples of -7, 2 is here. This is a line. I'll just abbreviate it. T times -7, 2. And if you go back to the videos I made right before we started the final exam, you'll see how this works in. You might even identify this as maybe the null space of a linear transformation, where this is the row space. In a linear transformation from R2 to R2 of rank 1, okay, and nullity 1. So it comes back to that. And I said a linear transformation, we haven't really talked about linear transformation. So this could represent a linear transformation defined by the matrix of rank 1 and nullity 1. Okay. In any case, this is how you find the space orthogonal to this space, because of course we've established that this angle is a right angle. Okay. So this is the line orthogonal to the vector 2, 7. Now, if you're in R3, debating about how much board space I'm going to use, because I don't know what I'm saying next. Just giving you an overview here, because we're getting into something new, so I'm kind of free to develop this as I wish. Okay. I'm going to need more board space than this. We're going to pose it here and then just talk about how it works out. Find V orthogonal to the vector 3, 1, -2. Okay. Well, then we're going to say that V1 is going to be some vector in R3, and I'm going to use x1, x2, x3 as the coordinates, because I want to get into subscripted coordinates, so we can generalize this to vector spaces that have more components than we have letters to represent them, okay? And I've talked a fair amount about how that works and why you want to do that, so I'm not going to get into it now. But okay, so your condition is V2 dot this vector has to be 0. Now, without writing out all the details, but it's obvious that, okay, well, V2 dot this is 3x1 plus x2 minus 2x3. And that has to be 0. Well, now you've got two free variables. And at this stage, things should be pretty familiar. Where do we go from there? Okay, we can choose any two of these, and that determines the third. Okay, so we're going to let S2, X2 equal S. That looks an awful lot like a 5. Let's see if I can get a little rounder. Okay, that's not a good S, but that'll have to do. Let X2 equal S, S3 equals T. Then X1 equals, could have chosen nicer numbers, but it's okay, they're not that bad. Negative S over 3 plus 2t over 3 so V2 equals S over 3 plus 2t over 3 S T. And again, doing something that we did very early in the course. This can be written as S times negative 1/3, 1, 0 plus T times 2/3, 0, 1. And that's fine. But I'm going to say we could also write that as, let's move this board over a little bit so it's easier to read. We could also write that as S times, I'm going to say 1, negative 3, 0. It's multiplying all these by negative 3. And that S is, the S here and the S here are connected by one being negative 3 times the other. And same with T. Going to multiply by 3 halves. I'm just going to multiply by the denominator. I'm going to say 2, 0, 3. Okay, well, the set of vectors with these conditions is the span of the set, negative 1, 3, 0, 2, 0, 3. And it's represented geometrically in R3 by these two vectors. And all the vectors that you get by combining them, and that would be the plane defined by these two vectors. So let's just go a little further with that, sketch that out. So I'll write it in set notation, the set of V such that V is orthogonal to three, 1, 2 equals the span of the set 1, -3, 0 2, 0, 3. And that span is easily visualized in R3 as a plane. So we come in here to R3, and I hope these vectors are going to be more convenient to draw than vectors usually are. So we have an x coordinate of 1. So that means we come out to 1 here. The y coordinate of -3, which means we come over here, -3 units. So right here, down in the xy plane is the vector (1, -3, 0). Then the vector 2, 0, 3. Well, you can come over 2 units here. So that would be about here. And then you come forward 3 units here. That'd be about here. Now that'd be great if that was the x coordinate, but it's not. That's a z coordinate. It's getting something that made no sense because clearly those two vectors that I was about to draw would span just the xy plane, and that's not right. So you come up here. Okay, so this would be the vector 2, 0, 3. Then you have the plane spanned by these vectors, the set of linear combinations of this vector and this vector. And you can visualize that plane. I'm not going to attempt to draw it. Picture get even worse than it is, but you see pictures, in your text and so forth. And if you understand where these vectors are, this one kind of goes this way, and this one kind of comes out this way, and you put a sheet of glass over that, and you get a plane. And this, of course, is a subspace of R3. Clearly, if you wanted to go to R4, if I had a fourth component on this vector, then I'd have to have a fourth component on this one. And what would I get? I'd get an equation with 4 variables. I'd have the 3x1, the x2, the -2x3, if I just added a number here. Okay, and then whatever multiple of x4, then I'd have to have, I'd have 3 free variables. And the 3 variables might be s, t, and u. And when I write out this condition, I separate this expression, the corresponding expression, into an s times one vector, a t times another, and a u times another. And then I've got the 3 vectors that span the 3-dimensional hyperspace of vectors that are orthogonal to whatever this first vector was. Okay. Another thing I can say about this is any vector in this hyperspace then is orthogonal to the original 3, 1, -2. So 3, 1, -2 would be like here, here, and then we'd have a -2. So we would have this rectangular solid down here. Hopefully you can kind of see where that is. And the vector goes from here down to here. And maybe I should draw that vector in a different color. So here is the vector. Three, 1, -2. And these two vectors are orthogonal to 3, 1, -2. You can see you do dot product here, you get 3, -3, that gives you 0. And here you get 6 and -6, that gives you 0. Any linear combination of these will then, dotted with this vector, give you 0, and it's easy to see that. I could call these just looking for a place to write it. Okay. Okay, the plane perpendicular to 3, 1, -2 is spanned by the set 1, -3, 0, 2, 0, 3. And this is a subspace. Need to write more. That plane is a subspace of R3 and it has bases. Well, just 1, -3, 0. 2, 0, 3. Okay. Note that these basis vectors are not orthogonal. It's not an orthogonal basis, but we can make it into one. And I want to see, they kicked me out of the website, I can't look. In an upcoming section, not too far along, I believe maybe the second or third section of this upcoming chapter, we learn how to make this into an orthogonal basis. So I'll say, but it can be made into one by this thing called the Gram-Schmidt process. Just involves orthogonal projection. Let's raise that up in case the watermark obscures it. I want to talk about projections, but we don't have time. That's enough. That's quite a bit, actually. And that should give you a background and a perspective on the assignment that I believe is due Tuesday, which will be, or maybe it was due today, that first section of chapter 5. Okay, so hopefully that's beneficial to you. I know you're going to concentrate on finishing the midterm between now and tomorrow, but then go ahead and try to get into that assignment. Because if your midterm looks okay, you're going to be in position to complete the course on time. And we're going to try to make that happen. Okay, very good. Any questions? Okay, Donovan. And I'll stop the recording.